see how that works. He's actually taking the bioinformatics specialization in computer science, so he's one of our first that's doing that program. They have to take a lot more like biological stuff and get the get actual understanding about of the bio side of bioinformatics. Um, Most of the people you'll find in the department are really just doing computer science with kind of most of their subject matter being bioinformatics. But for the most part, a lot of us don't understand the biology at all. So, but some of these other folks are actually learning the biology, and some of the computer scientists are actually learning the biology too. Just some of them inadvertently, just because they're doing so much with these things, they learn a lot about it. Um, so this paper is it actually concentrates a lot on a lot of the bio stuff. But what the reason I put it up there is because what's interesting about it are the algorithms and techniques that he uses. What he's doing is he's experimenting with different forms of different styles and hybrid mechanisms of clustering. Clustering is really just anytime you take data and group it according to, I don't know, some attribute that you choose. That's pretty much clustering. The whole idea is with a lot of these types of techniques, whether it's clustering or neural networks, SVM, support vector machines is another technique. All these ways are ways of classifying things. Okay, so clustering is really good for classifying things when you have when you're clustering for your groups might not just be like, for example, binary. SVM is a support vector machine is a very popular technique today to do binary classification, where you split things into two groups, and then obviously you can go from there and split two groups into three or four groups and split and things like that. But clustering kind of does it by, I mean, you can split into any arbitrary amount of groups, or it can be a a designed amount of groups, like with hierarchical clustering, where the clustering actually decides how many groups to put it into, or it puts it into all possible groups and you can look at it at different levels. What he's doing is he's building on some previous work of Wei Zong, Dr. Wei Zong now. He just graduated and he's got a faculty position. I forgot where he went, but he was doing something called he was basically finding what's called protein motifs, and motifs just being patterns in proteins on various attributes. So what he did was he looked at a bunch of proteins from all these different data sources they have, like the protein data bank and stuff like that. He pulled in a bunch of their attributes. Their attributes can be anything from stuff about their structure. It could be their sequences, that kind of stuff. He pulled in a bunch of stuff, clustered them together, and found that he could make the clusters form into groups that did things like that contained proteins that shared certain biological functions or biological attributes. Like some of the terms that come up a lot are like hydrophobicity or hydrophilicness, which is like how these proteins interact with water, and it can do things like it grouped them by structure information, by some of the other like kind of chemical properties of these things. And I'm really just spouting out stuff about biology that I don't really know a lot about. But what he found was there were significant biological things in common when he clustered them using things like sequence information. So that's very powerful, because what you can do is you can go get a protein, which is a sequence of amino acids, and just from that, with no experimentation or anything like that, put them into groups that might have attributes in common. So that's very powerful for biologists, because if biologists are studying, for example, some of these properties, these biological properties I mentioned, they might be studying one of them in the lab. But then this kind of algorithm, this kind of technique, would give them a whole bunch of other proteins that they could study and say, oh, look, they are all similar. I didn't have to go search through the millions and millions of proteins. I just searched through this small group that this algorithm spit out for me without any experimentation. So that's a lot of what's behind bioinformatics, is this idea of utilizing computers, all this data, do some computations, and then learn something about biology. Okay, because this really helps biologists, because biologists they don't deal with like nice clean little sets of data and things like that that we do, where we're just sitting there running algorithms, and we have computers we could just run algorithms on, and if it doesn't spit out anything, that's cool. It's just because that's just extra bits that we that we shuffled around, that it's nobody's loss. Whereas with biology, you're like sitting there dealing with physical things, and so a lot of these physical things are real ornery and stuff, and they could die, or like they could break apart or whatever. Like these proteins, when you're working with them, they can do all kinds of all kinds of bad stuff that our bits don't do. So that's kind of one of the biggest things behind this bioinformatics is we have tons of data, and then but we don't have the techniques for turning that data into useful information that the biologist can use. Another example would be not in a paper like this, but in another paper by Hai-Jin Hu. She does SVM, support vector machine. She does SVM to classify a type of protein called transmembrane proteins, which are proteins that they cross the membrane wall of cells. So hence transmembrane, they go across the membrane. Apparently these do big things, like as far as like they're like a way of communicating inside organisms. They're a way of communicating into the cell from outside the cell, which is very powerful because that's the basis of things like drugs, different pharmaceutical stuff like that. I mean, all that is basically communicating using these docking sites of proteins and cells and stuff. They connect, and then this kind of starts a chain of events, which I don't know, makes you happy, makes you sad, makes you, like all these different things that these pharmaceuticals do. So these transmembrane proteins, what she does is she uses SVM to kind of say, hey, it's transmembrane, hey, it's not. So she can look through all these proteins, and then these biologists have this small set of knowledge of what transmembrane proteins are, and that's mostly through experimentation. They actually go in and see these, like how these proteins behave and stuff, whereas she's doing it computationally. So what she does is, like in our meeting, she'll sit there and go, okay, here's what I did. I ran against this particular data set. I made this tweak because of this and this reason. And then like Dr. Ty, the head of the biology department, will sit there and go, cool, you just made up 100 experiments I could do on these proteins, and I don't have to go look for them and stuff. So that's the kind of stuff this bioinformatics is doing. This is a particular experiment in looking at protein sequence motifs. Wei Zong did some very powerful techniques that he did his dissertation on, and then Bernard is continuing some of that work by looking at different techniques. Okay, so what his new model is called FIT, which is basically a combination of two different prior techniques. One is fuzzy C-means clustering. Fuzzy C-means clustering is a clustering technique that uses some soft computing types of ideas to do fuzzy logic, which you've probably heard of at one time or another. Fuzzy logic is this idea of not just saying 1 or 0 for yes or no. You can have maybe at 0.5. There's like like if you're clustering, you can say it's not does this data point, is it a member of this cluster or not? It's this is this much of a member of this cluster. So then you get into situations where it's a chair, but it's also a stool type of ideas of where you can kind of put things into multiple classes. Okay, so what he does is he uses fuzzy C-means to break up the data, and then on the data that he's broken up into these kind of fuzzy C-means clusters, he actually goes through and iterates and runs through another technique, which the K in this is for K-means clustering, which was the basic technique we talked about before, where you just take the closest points to these centroids and then put them together. So what he does is he takes all the data, breaks it up into a smaller set of fuzzy C-means clusters, and then runs clustering on those. So the idea is that hopefully those K-means clusterings that are running on those smaller sets will produce higher quality clusters because they've already kind of been subdivided already, and then we can get more detailed. Okay. Whereas the previous techniques, a lot of them, like when Wei Zong was starting off with this stuff, he just did regular K-means on the whole data set. You start getting limited by how much you can do because the data set's so large and things like that. So this kind of two-stepped approach is just divide and conquer types of stuff. Okay, it gets so far as to actually go into some of the theories of granular computing, which is granular computing is usually again in the school of kind of soft computing, but it's a kind of a very fancy theoretical divide and conquer. Typical divide and conquer, breaking stuff up and doing stuff. The main difference is that the idea that the dividing isn't done arbitrarily. Okay, it tries to use what they call like knowledge-based division. They use actual knowledge of the pieces to help in dividing it up. When I throw around terms like soft computing as opposed to hard computing, soft computing usually starts getting into the world of like computational intelligence and artificial intelligence. The idea of, like these ideas of fuzzy neural networks, these things that are, and some SVM just because it's machine learning, but some of this idea of not being hard algorithmic, and sometimes not even deterministic, just go through these steps, and if it's this value, you put it over here. If it's that value, you put it over there. There's kind of more of a, I might learn that you kind of put it into this bin over here as opposed to you definitely put it in this bin because this formula says so type of thing. Okay, so what's interesting about this paper is that he goes through, oops, he goes through his technique and explains kind of how he goes through these two steps of doing the fuzzy C-means clustering, and then how he combines these techniques right into his complete hybrid technique, where he uses fuzzy C-means to create the information granules. He does this K-means clustering, and then he kind of merges the data. He merges his knowledge back together so that he has an understanding of the whole data set. Okay, so you can take a look at it really more just for seeing kind of some of these algorithms in action. This kind of thing obviously is breaking stuff up for us. That might be, again, another place where distributed computing, like what we're doing, becomes very powerful, because you can start running all of these information granules individually. That might lead to the potential to use more information granules or whatever. Okay, so the idea of what we're doing kind of more architectural computer science, where we kind of look at kind of the underlying structure of how we're doing the computation as opposed to the computation itself. And what we do is we look at some of these computer science problems, and we kind of say, hey, is there something there that I can do that I can exploit the underlying structure or architecture to do things either quicker, more accurately, maybe tackle larger problems, that kind of thing. Okay, so I put that up there. It's the last. I just put it under there, kind of outside of our other materials. Just at the bottom, it's called Paper on Clustering, and you can take a look at it. Okay, my hope, one of the things I'm doing right now, and kind of one of the main reasons for a class like this is, I want to use peer-to-peer to do this kind of thing, but I want to create a framework that we can do more general clustering type problems. So, like for example, in this paper, this is kind of the end result of a bunch of different attempts at doing better clustering. So the idea is, can we design kind of a generic clustering framework on peer-to-peer so that we can kind of swap in algorithms to try different algorithms and basically have almost like a library of distributed computation applications. Okay, so and that's mainly what I work on, is this idea of getting a bunch of these types of things, whether it's SVM, clustering, things like that, and writing small snippets of code or modules that you can plug into a generic peer-to-peer framework, and then kind of build an application such as this using those pieces. Okay, so just a little bit on what I've started in that regard. What I do is I kind of structure these distributed applications in like a tree, okay? And the idea is, and a lot of it draws from some of the ideas of some of this. There's some asynchronous computing methods where you typically when we run on a CPU, right? We take what is a machine instruction? What's a typical machine instruction? Like, let's say you want to add, right? If you remember back to like assembly, what do you do? Like, you want to add two numbers. and that will, yeah, it'll either accumulate it in one of the registry uses, or it'll put it in somewhere else, right? So the idea is you take some data, you load that data, you take some, you take an instruction, you run the instruction, and then that works on the data. Okay. There's some other kind of styles of computation. One of them is this idea of like data tagging, where you take the data and you take the computation and you kind of tell the computation that once particular pieces of data are available, you can kind of fire. So you can almost put the instruction first and then throw in the data, and then once everything's there, it'll fire. But see, the thing is, you don't have to put the instruction first. You can put the data first and then the instruction, or you can put one of the pieces of data, the instruction, and then the other piece of data. This kind of you're kind of free to do it however you want, and then the system is responsible for, do I have enough, and fire. Okay, so the idea is you have value 1, right, and you have value 2, and then you have an add instruction, right? So you kind of tell add, I need, you kind of give it a little thing saying, I need, I need value 1 and I need value 2. Once you have that, you can fire, and then you kind of say, oh, you're V1, and you're V2, right? And then if you put these in a bucket and shake them around, they'll eventually get near each other, and they'll say, oh, you're the value I need, you're the value I need, I'm firing, and I'll produce, V3. Well, that might be part of, right, another add instruction down here. So you keep shaking long enough, next thing you know, there's an answer down here that's all of your computation. Okay, so my hope is to do kind of a similar thing with, but not just on a chip or not just in a single system, but in a distributed sense where, for example, like with our clustering, I kind of broke down a very basic way of doing a distributed k-means clustering, like what we were looking at last time, is breaking up data, right, into these pieces where we can have things like D0, D1, D2, D3, and then the structure of the application would be something along the lines of, k-means module. So this is just a snippet of code that says, hey, you need a bunch of centroids and you need a segment of data in order to run this module. But then we structure the application by saying D0 and the centroids, all of them. So centroids, all the centroids that are available. Okay. So this idea would mean that you get the output would be some sort of D0 prime, right? A clustered set of data points which with their membership in certain clusters. And then you kind of say, well, if I want to do iterations, or I need to feed this into a module that moves the centroids, right? We went through an iteration of you cluster to all the centroids, and then you move the centroids to be better centers for those clusters, and then you do it again, right? So you keep going through that iteration. So the next one might be like a k-means correction, centroid correction. And for that, I need the initial centroid 0 and all the D primes. And then that will come out with a new set of centroids. Where does that go? Well, it goes back up here into another set of things. So this seems kind of convoluted to do it this way when you can just say, well, give it centroid 0, all the centroids, give it data 0. But it starts getting more powerful when you think of thousands of nodes doing this. Because now what you can do is you can describe the parallel computation, write a small module which has sequential pieces of code in it, and just track the data using your description, your overall description of the problem. Okay? So the description of the problem would be something along the lines of that, this going to another one, and then kind of another, oh, that's D1, right? And then another tree like that here. And then another tree like that here. But some sort of description to say, okay, this goes from 0 to n, right? This goes from 0 to m for the centroid blocks, right? And we're going to do this, replicate this 100 times for 100 iterations. Okay? So the idea here is that we write a very powerful distributed application by writing small pieces of sequential code and a map. Okay? So our language, our new language is kind of the map. Right? So what you can do is, in this peer-to-peer application, you load up one map, small snippets of code, and then the idea is that the system will self-organize and say, well, this module is being used all over the place. All these different nodes that are here need to download that. They can start downloading it from me because I'm the one who's sourcing it, but once somebody gets it, they can distribute it to somebody else. Right? And then we start leveraging all that available bandwidth. And then the map gets out there and says, oh, everybody needs the map, so everybody gets the map. And then you have to have a system of identifying these individual pieces so that all of them have the same idea of what D0 is. All of them have the same idea of what D1 is. And then you need a more complex system that says D0 prime doesn't even exist yet, right? It doesn't even exist at the beginning of the computation. It's going to be generated by the computation, but I need it to be universally understood by all the nodes. And even more importantly than that, how do I know that the D0 prime that somebody generated is a correct D0 prime? Okay? So that's the idea behind these kind of distributed systems, is how do we do that? How do we let them self-organize and let them create things that they're going to use in later parts of the computation? Okay? Anybody have any, just real, just off the top of your head, do you have any idea, if this is being generated by nodes in the peer-to-peer system, it's D0 prime, what are some techniques we could use to make sure that we're getting a consistent D0 prime? Because this is going to be deterministic. If you feed in D0 and all the initial C stars, you'll always get the same D0 prime. But what could happen? What are the bad things that could happen when generating that D0 prime? Do we necessarily control all the nodes in our peer-to-peer system? Hopefully not, because that gives us scalability, right? If we don't have any kind of formal interaction with these systems, and they can just join and leave as they like and be completely kind of autonomous, that's one of the powers of peer-to-peer. But it's also one of the weaknesses, because what could happen? It could leave and not finish. That's a separate problem, right? Because if it leaves, what if we assigned it a critical piece of this and it's not doing anything? So what's the best way to deal with that? Don't just assign it to 1. Assign it to 8. Now 7 of them can leave and we'll still have that piece of data coming out. But that doesn't handle another problem. One of the biggest problems on peer-to-peer networks, especially ones where the actors are, especially if they're volunteer or if they're autonomous in some way, or they're anonymous also. Okay? So I have this anonymous person coming in, grabbing some of my data, doing a computation, and spitting out a piece that other nodes might use in a computation. Okay? One of the worst things that could happen, and an easy thing that could happen, is this node that joins could just lie. Right? It creates a D0 prime that has absolutely no basis in the data. They're all member of cluster 1. That's what it spits out. Right? So, we have this wrong data. And then compare them, right? That's one of the most powerful ways of doing this in these kind of volunteer types of computing situations. Redundant computing, okay? Where you actually split up the data, you assign the same data and same kind of jobs to multiple peers, and then you can compare the results and kind of say, well, 3 people got the same answer, and this one person didn't. Well, I'm going to trust the 3 people because the idea is that if someone's going to be malicious, it's a lot harder to coordinate 3 anonymous peers to be malicious than it is to have one person be one peer be malicious. Are you always right? No, but if you can create a level of confidence that's very high, it doesn't matter that you're not sure. Because to be honest, you're not sure with a sealed symmetric multiprocessing system. There's always a chance that some sort of flaw in one of the chips or something like that could create wrong answers, an error in memory that ECC didn't catch, or something like that. There's always a possibility, but if we can get the possibility very low, then we're good.
So it doesn't hurt you that you're doing so much redundant work where it's almost no point in doing it over a distributed network.
Well, that's the other thing we have to balance, right? Because if all of them are doing D0, we're not getting any benefit, right? But if I have 1,000 computers and 10 of them are doing D0, I still have, I'm still 100 times the processing of the single machine. So that's the idea. So we have this additional problem of, gosh, I don't even know if the answer is right or if somebody's lying to me or not, right? But I also have 1,000 machines, right? Whereas on the cluster, I have 100 machines. So if I look at the two, if I can get a level of computation that's very high, I'm still doing better, right? And also, I didn't pay for any of those 1,000 machines, right? They're either volunteer or even if it's like micro payment in some way, or one of the other ideas that is out there, the idea of like you do computation for this job because in the future you're going to do computations for me on another job. So the idea is, oh yeah, I'll definitely volunteer my resources because then you can help me with my research, with my computation when I'm doing mine. Okay, but that kind of situation where you kind of say, I'm going to do this, then you do that for me. That's another reason that you should cheat, right? Is I can do. It takes me a lot less to do this D0 computation if I just say they're all in cluster 1, right? If I say they're all in cluster 0, that took me nothing, right? That took me going through and tagging all of them 0, right? Whereas actually doing the computation takes a long time. That's why we're doing the distributed computation. Okay, this is kind of into that next section of like whether it's incentives, security, trust, those kinds of things. There's some other papers on techniques for doing that. Okay, but the idea is we need a mechanism for that in a full-blown system, in a full-blown peer-to-peer system. We need some sort of mechanism for doing all of this redundant computation comparison. So if you make your language rich enough, you can actually build that redundancy using your language, right? The idea is this. Instead of taking it and calling that D0 prime, we actually reroute that. And we call that, D0 prime candidate. This is a candidate, so I'm going to go double prime, right? So this is a D0 candidate. I need 10 of these from 10 different sources, right? I need 10 of these to go into a compare module, right? And if at least 6 of them come out with the same thing, then that actually spits out D0 prime. And then I can fit that into here. Right? So now the data tagging, the required elements now becomes I need 9 other D0 double primes from other places. Questions?
You need 9 other D0 primes?
Double primes.
Why? Since you have 10 right there.
Well, I have mine.
Okay, so you need 9. Okay.
Right. In fact, that's not true. Actually, I need 10 of them. Even if I didn't do this, I might do this. Which, I don't know. You could do it. I mean, if you have a cluster of machines, you might dedicate one to just running this compare operation. Who knows? Right? But, yeah, you do need 10 of them. But my idea was that you had one. But that's not necessarily true. You could just say, I need 10 D0 double primes. Pull them from everywhere, compare them, I didn't even do a clustering operation, and I'm the one with D0 prime, right? I'm the one with the actual D0 prime. Okay, and then you plug it into the next one too, and then the final answer when you're bringing them together, you do that. Anytime you're generating data that's going to be used in further computations, you run it through this compare module. Okay, this is the type of thing like these types of ideas. I see most of these in things like because I do a lot of public computing research. Things like SETI at Home does this, where they'll go and whatever the work units you're working on, they'll actually redundantly do it on multiple peers and then compare them.
Who decides who it's going to compare? Like if it's just a totally anonymous.
You don't, and that's the idea is you put it out on enough machines that even if people collude, they'd have to get a large amount of collusion. In other words, have to get 10 people, or actually in this case 6 people, to fake the results. So, and then you start running into the idea of, well, what if somebody just creates 10 fake nodes and joins them in and stuff like that? You might be able to do that, but one of the limiting factors is things like you register with, they keep track of all the different participants, and like if people are popping up with erroneous nodes or something like that, they might cut them out, and then they have to rejoin and stuff like that. So the idea is that you can't solve the problem, but you can make it so that the effort you need to put forth. The idea is make the effort harder than just doing the computation, right? And then at that point, it's just straight maliciousness. And if they just want to be malicious and game your system, there's the potential for that. But hopefully, you'll hit enough of the other nodes that you can catch people like that and cut them out. Okay. Eventually, you're cutting out their whole class C, and now they have to go to another provider in order to game your system. Something along those lines. Okay. It's like anything in security. It's not really you don't have to stop somebody from stealing $100 from you. All you really have to do is make it so that it costs them $101 to steal $100 from you. Okay. I mean that's one of the things, and that's often a lot easier to do, and it often costs less than $100. Because if you're spending $100 to save your $100, you're also doing something very wrong, right? But I mean, it's those kinds of forces that we're talking about here. Okay, and I mean, the idea is that yes, we'll do all a lot of things like a lot of the things that we see in traditional like information security, like signing things and stuff like that. But signatures and things don't help us here, right? How do we sign something to verify its authenticity when we don't even know what it is, right? It hasn't even been computed yet. Once we get this D0 prime, yes, we sign it, right? We sign it and say, I vouch for this particular D0 prime or whatever. Okay? And then enough people vouching for the wrong thing, you shoot them out of your system. Okay. So, let's look at chord. Everybody get a chance to read it?
Yeah.
Okay.
I don't know if I call it reading.
Oh yeah, so that's what we're gonna do here is everybody at least accepted the words into their eyes, and we'll go through and see if we can. I think it's the bottom. I'll try reading it. Yeah. Looks like it did. I think no. It should start humming. There we go. Is it doing something?
Yeah, I think it's solid.
Had it working. Or if it needs a while for it to kick it. It's been sitting there.
Oh, it sounds
Oh! Alright, here we go. Yeah. It's proceeding to be broken now. Alright. So, chord. Chord. Okay. So, what does chord do? What's its main? I mean, what's it has a very 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 specific purpose.
It hashes the keys. It gives it takes the IP address.
Go back from that. We're not talking about how it does it.
All right.
Search for what?
Data. Just data. Anything values. Hash.
Searches for hashes. Why? Where are they? They're distributed among nodes in the peer-to-peer system, right? So we're searching for keys. That's it, right? The idea behind chord is I can take a bunch of systems with arbitrary addressing and find keys on them. Right? And I also describe how to store the keys, where to store the keys. Okay? And associated with each key, actually it's not even chord's job to associate data with it. Right? All it is I can find a node holding a key. Okay, so now that's all it does. So now let's get back to what's the idea here? What's a key? No. It has to be something. It has to be something very specific. No, it's not an IP address. A key is what? It's a number. It's a hashed value, and it has to be a particular length, right? As far as bits go. So a key is a number. That's fine. Okay. So this system now, we've added to it. A key is a number. I can choose any number that fits in these bits, and I can find out what node is responsible for it. Okay, that's cool. So, does that alone, just having numbers and knowing where the numbers are, does that get us to, for example, searching for a value associated with it? Again, disregard the fact that chord isn't technically responsible for tying the value to the key, but I guess my point is this. I have an application and I want to search for a keyword. Okay, I want to search for, I want to search for networking as my keyword. With our system so far, keys are a number that fit certain bits, and chord is responsible for making it so we can find a key on a node. Let's say we can do that. Can I find the keyword networking? With associated value with what?
With the key. Like if you have a key instead of the key associated with networking, then you can use chord.
There we go. That's what we're missing is how do I associate a keyword like networking with a key? So how do they do it? Right, with hashing. Okay? So, hashing is what? What's the idea of any kind of hashing?
Take a large set of values, be able to put it in like a smaller set.
Okay. So the idea is taking a large value and putting it into really a fixed set, right? A fixed size value. Okay? That's the only requirement for hashing. And actually that's the only requirement for chord, really. But if you don't do it right, chord's not going to work very well. Okay? But the idea is this. You take an arbitrary amount of data, right? With size n, right? Any n. Send it through some sort of hash function, and then what comes out will be a fixed size, m or k or whatever. Okay? So, what are the issues that come up when hashing? Collision. What's a collision?
Where two of your size and values can form the same hash values.
Right. Okay. Can we eliminate the problem of collision? No. We can't. right? Why is that impossible? It is impossible. Why is it impossible? If it's possible to eliminate all collisions in a hash function, you have created the perfect compression function. Why? Because if there's a one-to-one mapping from any value sent into the hash to any hash that comes out, you can compress anything. Just know the mappings, right? Now, the hash value represents directly the value that you sent in. Okay? So we cannot eliminate collisions. Okay? But what can we do? No. Oh, you're talking about the concept of like a hash table. That if we do collide, then we need some way to compensate for colliding. But just in the function itself, what's a good hash function?
Just ensure that K is sufficiently large.
Well, that still might be a bad hash function. If we have a K that's very, very large, we can still collide if our hash function's bad. So a good hash function means what? Whatever we send through, the least possible likelihood that it's going to collide with another one. So how do we do that? We make sure that any value we send through, that we generate all the hashes kind of uniformly. In other words, any value you send through has equal likelihood of becoming any of the hashes that come out. In other words, we kind of want to make it so that we use all the keys, because the more hash values, the more hash keys that come out, that's how we maximize the likelihood that we're not going to collide, right? That's the best we can do. We can't make it so we don't collide, but we can make it so that we use as many of the values as possible so that we have the least likelihood of colliding. And then, once we have that mechanism in place, then we increase the key size to make sure that the larger we make the key now it does have a use, right? Because the larger we make the key and we're equally using all of them, we're actually adding in kind of more space for all the values we're sending in. Okay? Cryptographic hash functions usually have other properties. Things like it's hard to predict what the hash will be. Right? The other thing is that small changes to the input will avalanche down into large changes in the hash function. That's very important for cryptographic hashing, because you don't want somebody to be able to take a contract and change 1,000 to 1,000,000 and then hash it and it comes out the same, right? And you don't want to be able to predict what the hash should be, because then somebody could sit there and manipulate the input. The typical technique is to add white space or something like that, or invisible characters, so that even though your file has 10,000 more characters in it, it still looks the same when you print it out or whatever. So your super big contract that you're signing with a digital signature has a bunch of embedded invisible tabs and backspaces and things in it, so that when you print it out on a printer, you're still giving them $1 million, but but the actual data is different, so the hash can be the same.
Isn't another importance that it's one way, that like you can't, by looking at?
Well, it has to be one way from our previous property. If multiple things can become the same hash, that's the one-wayedness, right? Because if we don't have a one-to-one mapping, we can't go back, right? So that's kind of a side effect of the other piece. Again, if you can go back, again, you've created perfect compression, which would be cool, but doesn't help us in our particular problem. Okay. So now we have a hash function. How does this help us? Go back to our previous example. I'm searching for networking. What do we do? Hash what? Hash networking. So what we do is we put in a string networking. Right? We send that through. That will come up with a hash value. And then that hash value is our key. Right? So then we already said chord can take a key and make it be a node. Right? So once we have that key, we could say, hey node, you happen to be responsible for networking. right? It might not know that, but if there is a key networking, that's where it should be, right? And if it's there, what can we do in a higher level of software? Like if I'm searching for networking and I get a key that says, this is the key for networking. And now I've gone through chord, and chord says it's on node 2, right? Or whatever. So now we're on node 2. Design the software that, now that we're sitting on node 2, what do?
What were we doing again?
Huh?
We were just asking for network.
We were trying to find the keyword networking. So I don't know what our applications do. It searches for research papers. We have research papers with networking.
I think they asked Node 2 to give me some research papers about networking.
Okay, so what would we likely put on node 2?
Research papers about networking.
Maybe, but that has a problem. If we actually put research papers on networking on node 2, we're not really taking advantage of our peer-to-peer. So what do we put on there instead? How about this? Keys representing papers on networking. Maybe file names or whatever. Okay, so don't store all the network papers there, right? Get a file. This is my networking, right? We'd actually be smart and actually just have that be for the key, right? Because we never even need to know that it's networking, right? It's just the key, right? And then we can say, we don't even have to store the keys of the papers. We could just put the names of the papers or some file name or some identifier, but chances are we just have key 1, key 2, key 3, key 4. And then, so when we search for networking, we go to this node, and it looks in its file and says, okay, I got key 1, key 2, key 3, key 4, so what do we do now? We do the same thing, right? We tell chord, I need key 2. Chord will find key 2, and then now we store the paper on with key 2. Okay? There's only, I mean, what do you think the main reason that I suggest that we do that instead of just storing all the networking papers there? Right, so like as far as like replication goes, right, we'll still need that in all of them though. Like whether we replicate the spot, we've actually increased what we need to replicate now, right? Because now not only do we have to replicate the papers, we need to replicate the list of papers and stuff like that. But the thing is we eventually get to some data. Okay? One thing that would happen in our system if we stored all the networking papers there is what? Right, so if you're searching for networking, chances are you're going to be downloading a bunch of networking files, of these papers, right? So now what you've done is you've made it a one-stop shop for you to use up all the bandwidth, right? Whereas with this indirection, we talk to it, we use a small amount of our resources to get that list, and then we can go through and grab those files from various nodes, okay? Even better is maybe we have title information here, right? So we can go get that, look at the title information, and decide which ones we want to download. Okay, but that's all higher level stuff. But the idea is we want to try and avoid places where too much can go on at one node. Okay, so like a little bit of indirection is helpful, but we can't overdo it. If we keep doing indirection stuff, every time we want to get a networking paper, it's like 8 different nodes that we have to talk to. We're really inefficient. But maybe a little bit of indirection might be helpful. Okay? So, knowing what we know about the properties of our cryptographic hash function, and let's say these keys are keyed on the file name that I guess the file could be stored as different names, but however we generate the initial, like if the first person to introduce the paper into the network, its file name is what the key ends up being. People are welcome to rename it whatever they want, but they just need to refer to it by its identifier. Okay? But knowing what we know about our cryptographic hash function, what do we know about where all these papers are stored. I've done this list, and I've keyed the papers of this list by their file name, right? And then chord now, we already know chord knows where to put these keys. Knowing we know about our cryptographic hash function, and later when we talk a little bit more about how chord stores these keys, how many systems do you think those 4 papers are stored on? Do you think all 4 of them are on one machine? Why? They could be, but why? But why do we not think of this? About what? Well, we don't want them to be, but I'm saying, do we get that property just knowing what we know about our cryptographic hash?
No, they won't be.
They won't be what?
They all won't be on the same one because it's a good hash and it spreads it up.
Right. So basically, if chord is designed well where it distributes the keys, and we know our hash function spreads the keys around, spreads the values of the keys around uniformly, then we know that transitively we spread these papers around on the chord network. And that's what chord wants to do. Okay? That's what all this theoretical stuff that they refer to all these theorems that they prove and auxiliary papers and stuff like that. Most of that stuff is talking about these properties of consistent hashing and spreading these keys around. The idea is that they easily get this property by the fact that the nodes on a chord network are keys themselves, right? Using the same mechanism. So if the keys of the nodes are using, like SHA-1 in their case, right, a cryptographic hash function, they'll be spread. The keys are using SHA-1, they'll be spread. And since they're both being spread, they're both, all the keys are going to be distributed around to all the different nodes. Okay, questions on that? Okay, so how do we do it? How do we make chord spread all this junk around? Membership in a chord network. What does that mean? I joined chord. What does that mean? I've joined a chord network. Does it mean I have an IP address? I had one before. I was on the internet before I even thought about joining a chord network. Right? It means they can talk to me. They could talk to me before, right? Because I was on the internet, and they're on the internet. What's that?
They have links to it now.
They have links to me. How?
Like if you join and then you become the next node for I think you joined in instead of the previous one.
Right. You get inserted into this chord, this ring of chord nodes. So essentially, joining a chord network means, hey, I want a key. Right? I want a key in your network. Right? So how do I do that? Well, chord uses what to identify the nodes in its network? What is a key on? I think they mentioned it. Yeah, it's probably IP address. Yeah, they hash the IP address. So they take the IP address and then they hash it. Why? And they hash that IP address and then that becomes your key. In other words, the hash of your IP address is your basically key identifier, your key that identifies you on the chord network. Okay. What's the benefit of hashing by IP address? Right. They're unique at least at the view of the from the view of the internet. If it's not unique, you have bigger problems on your hand. You can't talk to you can't deterministically talk to anybody else on the network, right? Because if you have a duplicate IP address, IP doesn't know how to route to you, or at least it doesn't know how to consistently route to you. So that's another problem that you can solve before you even start getting involved in my chord network, because I need to be able to talk to you because I'm not handling the actual network communication, right? But you join in a chord network, you say, hey, here's my IP address is this. I'm going to hash it, and then here's a key, and you say, hey, chord network, this is me, and I want to be put in. Okay? So, what's all this business about a ring and successors and all that stuff? Yeah, that's where it starts getting. That's where the hard part of chord comes in, right? This idea of how do I use this ring idea? Okay. Now, the first thing that you need to think of is a hashing function. What does that have in common with a ring? What does that have in common with a ring? A hashing function, the output of a hashing function is a ring. Dun, dun, dun. It doesn't have to, but because it's fixed, right? Because it's a fixed length of bits. Okay, we're going to use modulo arithmetic to get it smaller. Okay, so because if I have a fixed length, if I have 2 bits, what's my ring? Huh? 0, 1, 2, 3, right? Because when I get to 4, I have a problem. I don't have any more bits. Go back to 0, right? So, and then my 4-bit actually gets overflowed and thrown away, right? So, I have a ring with this hash function. SHA-1 typically, what, like 168 bits or something like that? That's too big. Okay? So, what can I do to make the ring smaller? Modulo arithmetic, right? Anything modulo is a ring. Right? And modulo just means, when you get to the last value, come back around. Right? And then keep going through. Add 1, add 1, add 1, add 1, add 1, and then you'll loop back around. That's our ring. That's our chord ring. Okay? In this case, though, the values are the keys, these hashed values that we're putting in there. So the idea is create a ring by hashing our IP addresses, our identifiers, and then placing them on the ring. How do we place them on the ring? However big we want our ring, right? We just do modulo on the key, and that's where it is, right? Modulo is like a hash, right? Because any number that you send into modulo arithmetic will come out within the ring, right? So I can send in as many bits as big a number as I want, and modulo will bring it down to scale of my small ring. Okay, so they have an 8-node ring, right here. How do I place myself in the ring? I hash my IP address, modulo that key, and then that's where I fit in. Okay. I don't recall reading anything in court about clashes with join membership, and I think they just use a large enough ring that they don't, or that it's improbable that you'll get a clash. Now, I don't know. I'll have to go back through, but they might use the whole 168 bits and make just that big a ring. But they also talk about some other techniques for putting virtual nodes on there to spread keys out even more. So they're balancing something with how big the ring is and how consistently you can make sure all the keys that would go into the space get spread out. Okay? But the idea is you come in, your key gets inserted into the ring wherever it falls in this, using this modular arithmetic. Okay? So that becomes your kind of place in the ring. Yeah.
They did say that they had a problem with it, so they decided to use the entire 4 million IP addresses as their ring size.
Oh, okay, yeah. All right, so they use 32 bits as their ring size, because 32 bits would cover all of it. Okay, yeah, they do. Oh, okay, yeah, I do remember that part where they talk about having enough nodes. Either that, or they make sure that they use that. They mention that that's the maximum amount of nodes that they need, And spread onto a 168-bit cryptographic hash function means that it's next to no possibility that you're going to clash. And that's true. Because 168 compared to 32 and a good cryptographic hash function like SHA-1, you're good to go. Okay? So we have a consistent way to pop things into our ring. Okay? But that's not enough. Okay? So what we want to do is place keys, other keys outside of our IP addresses onto this ring. Okay? We actually are more interested in placing them on the nodes. Okay? So there's a problem. Our ring is so big that chances are we don't have somebody in every slot. Right? Well, actually, let's go back one. Let's say our ring is full. What node should a key go on? If I have a keyword like networking, what node should I put it on? I said the ring is full. It's kind of counterintuitive considering we're talking about hashing. The basic idea is you put the key on the node that this key, on the identifier that this key collides with. What do I mean by that? It has the same spot on the ring. In other words, you take this key, find out where it goes on the ring, and that's the node you put it on. In other words, the collision between your key and the IP address identifier hashed by the node that's in that spot is where you live. Right? All right, so that's where I put the key. They're done. Chord's done. Okay? Now, the problem is, what was my stipulation when I asked that question? The ring was full. Is the ring full? No. And in fact, we've already just stated that there's all kinds of factors that say it is impossible, almost impossible for the ring. Actually, with 168-bit hash, if you're using the whole thing and you're using 32-bit IP addresses, it is impossible to fill a ring. So, we have a problem. The ring is not full. So what do we do? Go to the closest one. In fact, we go to the closest next one. Right? The successor idea. So, instead, what you do is you hash all your nodes, you put them on the ring, you hash keys, and you put them on the ring. If there's no node there, you keep going until you hit somebody on the ring. And then that's where you're supposed to go. Okay. Chord's done. Right? But in order to do this ring, what do we need to keep track of?
Where that value is. I mean, what if there's a big gap, like, there's a big space, and then you assign a value and it has to jump all the way to this
We have a more fundamental problem than that at this point. Is there's no ring, because we know how to place them on the ring theoretically, but how do those nodes talk to the next person on the ring, no matter how big the jump is? Because right now what we're doing is this. Is in order to find the next spot on the ring, can we just say, oh, well, 1 plus my key is this, right? I still haven't gotten anywhere. Why? Me knowing the next key value, does that help me at all in contacting a node? Why? Even more fundamental than that. Can I talk to keys on the internet? I have to talk to IP addresses. Can I find out what the IP address is by knowing the next key? No. So what do I have to do? I need to hash all the IP addresses and find out which one has that hash value. Then I can try talking to it. And with cryptographic likelihood, there will be no system at that next node. So what do? I go to the next one and find out. Okay, so I have a problem. Is even though this theoretically I have this great way of putting everybody in a ring. I got this great way of putting keys onto the ring. I have a problem because I can't talk to those keys on the ring. So what do I need to do? Keep up with your next person, your successor, right? So what you need to do is when people join, you put them on the ring, and you say, okay, you need to remember the person after you, and really you just have to know the person after you. You don't have to. And one of the key things that they're talking about is successor pointers, fingers on their finger table. That is the only required correct values, is the successor. Why? Because we end up with a ring. Okay? We end up with a ring by a node inserting. This one updates its successor to that. That one updates its successor to that. Okay? I can't just say my successor is this and store that value. In other words, in my finger table, I can't just say, if I'm node 1, I can't just say node 2 IP address. Well, yeah, I can. I need to know what their key value is and then their IP address. Because I need their key value because I have my key value and I have their key value. What does that create? If I know my key value and I know my next person's key value, what do I know about all the keys in between those two values? Right. In other words, there's no node between those two values. Right. What I've done is I've created an interval between me and my successor. If they have an interval between them and their successor, and so on, we've now covered the ring. Right? So let's join node 1 into this ring. So before we do that, what is node 0's? We're just doing successors. Okay? What does node 0's successor table look like? Right, with node 1's not there. So take this node out. What does its successor table look like? The next node is 3, so what is the interval? 0 to 3, right? So that's what this notation they were using is. Not including 3. Everything between 0 and up to 3, but not including 3, there's nothing there. 3 is responsible to it, so IP address of 3. That's what its table looks like. What does node 3's successor table look like? Right. Join node 1 in. First of all, what does node 1 need to join? Not yet. It has an IP address, yes. So we need an IP address, and we need to hash it, and we need a key. What does it need, though, to join this chord ring? It needs to know somebody in the chord ring, right? Otherwise, who does it talk to? So, who are we going to talk to? Let's talk to 3. That's more interesting. So talk to 3. I'm node 3. Hi.
Who's your successor?
No.
Who's your successor?
No. You're a noob. You don't know anything about my ring. You don't know anything about my ring. What do you know?
You're on it.
You know your IP address, and you know I'm on the ring that you want to join. Okay, so do your own work. You hash your IP address, and you tell me your hash value and your IP address. So you tell me my IP is this, right? And your key value is what? Here's a hint. Your key value is 1. I'm node 3. What do? I say, oh, okay, you're key 1.
So you know it goes before you. So
No.
you go around the other way.
Right. The only thing I know is that it's not in my interval after me.
So you go
To where?
0.
To 0. I go to, I say, these intervals, it's not in that interval. I don't have anything else. I have no idea where this person goes. So what do? I say, hey, node 0, I have your IP address. I'm going to talk to you. I come talk to you and I say, hey, node 0, I got this guy 1. He wants to join. So he takes 1. He takes his IP address. So now we're on node 0. What does node 0 know? It's inside the interval. So what do? So I know he's my new successor. Okay, so you can tell node 1, hey, you're my successor. My old successor is your successor. Great. So now, what does node 1 do? It has to build its table, right? So it says, I'm node 1. There we go. What does node 0 have to do? Redo its table. So what's its new table? 0 to 1. So before we do that, we say, hey, IP of 3 is key 3. We tell it what our old successor was. Okay. So 0 to 1 is now our interval, and our successor is 1. What does node 1 have to update to? 1 to 3. And we know the IP of 3 from... And we know that 0 is... It knows what the interval is, and it knows that 3 is the next node, because if it didn't, if there's something else there, the ring's already inconsistent. Right? As far as what the ring looks like now, that's what it looks like. Nothing between me and 3. So now our new ring. Perfect, right? We got the whole ring covered with intervals, and everybody knows who their successor is. That's chord. All of chord works now. So, why do we have all these other pages? What's the main reason we have all these other pages? Failure's one. But even more, bigger than that right now, what's the problem with our ring, with our chord? Our chord is slow. Right. What's chord? Log n. Log n better. Right? So log n is a lot better than n, especially if we're talking about tons and tons and tons of nodes. Okay? How do we get log n with chord? Keep track of what? Not just more. Very, very, very particular nodes. Right? We keep track of nodes. The idea behind log n of chord is you want to split the distance every time you check your finger table. Anytime you see log n, one of the first things you should think about is halving. Right. You want to get big jumps. Okay? And you don't need to take care of anything more than half a jump, half the ring jump. Why? Because anything more than that, overshooting by that half, is a waste. Because you're probably not going to hit exactly where you need to go with more than half, right? But if you just do half, you can just go to that node, and then it's got half. Well, you've already quartered it now, and then the next one, you're 8, and next thing you know, you're logging in, which is great. right? Because now you can jump all the way around the circle and get to a point that would have taken you linear, right? Which would have taken you in our system going through every successor, right? So that's the beauty of chord. Okay. The other thing is that it's simple, and the other thing is that we have failures, we have joins, we have simultaneous joins, we have simultaneous, exits, stuff like that. So that's what the rest of the paper is all those different details, and then also this finger mechanism to split distances quickly. Okay. So the idea is, just by knowing these intervals, we can do stuff like splitting distance and things like that. We just need to know where we fit on the ring, and then we could just, does there have to be a node halfway across the ring? No, because there's going to be a successor that's responsible for that point. So no matter what I do, I can split at least the key space, and if my key space is uniformly distributing all the keys, then I'm effectively splitting the network size, right? In other words, if I can go to the halfway point of the key space, the cryptographic hash says I'm going to halfway point of the network. In other words, if the keys are uniformly distributed across if the nodes are uniformly distributed across the key space, splitting the key space in half, chances are I have half the nodes over here and half the nodes over there. Okay, and splitting the distance like that, very, very good. We don't have to store that many addresses. The more addresses we have, the quicker we can get to specific points of the ring. But if we do that too much, yeah, searching the list takes longer, and then even more than that is the list gets too big. Because if we're growing this to thousands to millions of nodes, you don't want to keep track of a million. I'd rather keep track of 2 addresses than a million addresses, right? My successor, and then a halfway point around the ring. And that alone will give us very good performance if we can binary search every time. Okay, so joins we've seen, right? We just did a join, and the only addition to the join now is we just update our finger table when we join by doing that halvesies thing, right? They have another issue that comes up with the joins. I find my location on the ring, and I change this interval, right? And I change my my predecessor's interval at that point. What impact does that have on the rest of chord, changing that interval? Like, for example, 0 changed from 0 to 3 to 0 to 1. How does that impact the rest of the chord system? I'm not talking about the rest of the network, but what other responsibilities have just changed? Who gets what keys, right? Because you're responsible for the keys in that interval that you're the successor for, right? So if you change the intervals, you've changed what keys reside on you. So what do you have to do? Yeah, you have to basically migrate the keys off the previous successor of those keys and move them onto you, which is good because now that you're joining in, you take some of the load, right? That's, if you want to, if you're going to come join our network, you better do some stuff. So when you come in, we take some of the keys and then move them over. Okay. Some of the very powerful aspects of chord, they go ahead and show that the maximum, like, there's very high likelihood that you're only going to move a few keys, right? Because you're moving a fraction of the keys off one of the successors. Another thing is that you really just talk to one system to move keys. Okay. Another problem is the fact that keys uniquely fall onto one of the nodes. So at a higher level, what we want to do is replicate a lot of keys. But we can't replicate keys because the cryptographic hash function is responsible for putting them somewhere. What's a simple way to solve that problem? .1, .2, hash those, right? So you take the keys, you add in, some sort of additional piece of information that says this is replica 0, replica 1, replica 2, hash those instead, and those get distributed. Right? So you have to do tricks like that to make sure that you get a different key. Getting a different key will move that somewhere else. So now you have a replica. So what happens? Well, a node fails. All its keys fail with it at that point. That's bad, right? Because all those keys now, if we search them, there's no node to go to. So what do? You go to replica 1, find that, and then maybe drop some information. Hey, you know what? Replica 0 is down. I just tried to look for it and it's gone. And they'll say, oh, okay. What I'll do. So how do you restore replica 0? Right. You create a replica 0 again, and then where do you store it? Where it now goes, right? If a node dropped out, something else is now the successor, right? So you create replica 0 and then just pop it on the network. As usual, you say replica 0, done. And then it'll go on and find the new correct place. You do that enough times, the new successor now looks like the old successor. Okay? But we have not put that onto as a burden for chord. Chord's simple. Keep simple, right? Keep all that simple because all this replication stuff, all these additional features, you can just use the same chord mechanism to handle all that. And that's a strong system that's very, very flexible like that, that you have enough of the primitives you need to do all these higher level functions. Okay? You leave it to the higher level functions because the use of this chord network might be completely, you don't know what the uses of this chord network are going to be. So you can tailor those replication problems, stuff like that. You can tailor all those things specifically to your application or to your use of that network. What other things came up in the paper? What else do we got? Scalable keys. So this is the update, the more complex finger tables. Okay, actually, how about this? What are some of these? Here we go. This is a pretty well written paper. They do very good techniques when writing papers are things like just frankly just saying what are the bad scenarios, how do you address it in individual scenarios, not getting into this convoluted, I'm going to answer every question with this convoluted theorem and explanation of a theorem, but giving the here's the 3 bad things that could happen when you're joining, and here's how chord addresses all 3 of them. One of them we can't handle, but whatever, right? But the 2 more likely ones, we handle, right? And here's worst case scenario. So, if joining nodes have affected some region of the chord ring, a lookup that occurs before stabilization is finished. What is stabilization in chord? It's mainly updating the finger tables. You join, and basically you get a correct, you correct you add in your successor, and the person that kind of joined you in at the point where you insert into the ring, they've updated their successor table because you actually had to talk to them and say, oh, I'm going in here, right? So you have the successors fixed. Stabilization is really is equalizing the rest of the finger table, right? The main reason is that just having correct successors makes the chord consistent. The chord works. Okay? It's these optimizations for splitting distance stuff that gets broken. So stabilization is a periodic thing that they do to kind of refresh those optimizations. So they point out the common case is that all the finger table entries involved in the lookup are reasonably current, and the lookup finds the correct successor in O log n. Right? We find it in O log n because our finger table is good. We can split the distance, split the distance, split the distance, find our spot, pop ourselves in. Okay? The second case is where successor pointers are correct but fingers are inaccurate. Why do they say that this is not a failure? It takes long because we're going through successors. We eventually have to drop back to using successors, which is linear. Right? So they're saying It's correct but slow. Perfectly acceptable, right? La, 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 la. In the final case, the nodes in the affected region have incorrect successor pointers, or keys may not yet have migrated to newly joined nodes, and the lookup may fail. That's our bad scenario, right? So, the higher layer software using chord will notice that the desired data was not found and has the option of retrying the lookup after a pause. Why retry the lookup after a pause? Stabilization would have occurred. Finger tables are now consistent. A second search will find it. Okay? Now, that's pretty good, right? So, a fairly consistent network, we join in, and everything gets consistent in O log n. Awesome, right? We join in, finger tables not necessarily consistent. Worst case scenario, we're joining in ON. Okay. The fundamental underlying necessity for correct successors is wrong, and we have a failure that will be corrected by stabilization. Bad, but not bad, not that bad. Right? That's good. And then they do point out some additional kind of highly, highly theoretical scenarios of what? Of completely, they're saying that there may be scenarios where multiple joins at one point can create essentially can essentially sever the network and create cycles that are outside the network. What does that mean? Well, if you do a theoretically potential set of joins that would make it so that the successors are so broken that you kind of make multiple chords. Okay? But the probability of that is so low because, especially because of what? These finger tables have pointers going into to skip jumps. So chances are you know about nodes that are outside your ring, and you can discover the network's been severed. You see what I mean by that? If you have enough joins that you sever the network, if there's no information from one to the other, then yes, you've broken the chord. But you've actually created two consistent chords that work, right? But if any of the information goes to the other one, you could eventually, at a higher level, discover that the chord's been broken. And that's what they're saying about this. At a higher level, you can look for those. In other words, go through your finger table and talk to stuff and say, are we even on the same chord? type of thing. And if you ever get a actually, no, we're not. And then you can go in and call for basically just rejoin one of the members of your ring, and then you should be able to. In other words, if you can get that other member into the ring, then they'll find an inconsistency and then put everybody where they're supposed to go. Does that make sense? So the idea is that they have bad situations, but they address them, which is good. This is an interesting point here. When they start going into their simulation, somebody explain to me the statement that they make here. The chord protocol can be implemented in an iterative or recursive style.
Either the query node makes all the requests to each new node, or the request is passed through nodes.
Okay, so what we do is, in the iterative style, one person is responsible, and they ask for data from the other nodes. In other words, they're just using their tables, right? Their finger tables to find successors of them. And then the recursive style, like you said, is I'm looking for this. And then here's my IP address. Here's what I'm looking for. Here's the request. So then that next node will look through its table, find the next hop that it needs to make, send it there. It looks through, finally finds the successor of the key you're looking for, and then that node will then talk back directly to the source. Right? Pros and cons. What are the trade-offs there?
Iterative, we'll be able to find out a lot faster if a node's down on the list. Or something. Or fails, or search fails, I guess.
Yes. Maybe. Depending if you report back at all. No. I mean, because the first node that fails would send back error. In other words, if you're hopping through and somebody in their table says, "Oh, the node I'm supposed to talk to isn't there," or whatever, or the node that you're looking for isn't there, you'd still have to go through the same steps. In other words, that would be the reporting node back to the source. Faster in the sense that there's less overhead of talking to another machine. Well, no, you just have to talk to all the machine. No.
So wouldn't recursive would balance the work amongst more computer or more machine or nodes?
That's the main thing, is that you're distributing the call. In other words, the search. The search is now spread across all of them. In other words, you fire and forget and never see it again until something reports back error or you get your results. And hopefully everybody's playing nice and they'll report back results, right? So, but if they're not, I mean, that's another potential, is the fact that they do have the potential. If somebody maliciously stops the query, then iterative would find that and the other would not. So in that case, you do get faster response. But only through maliciousness. In other words, only through failure of maliciousness. The only case that a failure is found out more quickly in iterative than in recursive, if it's not malicious, is if the node fails while it has the request. Right? If somebody sends it the recursive request and it says, "Oh, let me go look at my table," right, and then it dies right in the middle of it, then the request is lost. Right? But you distribute the load of the search rather than one node being responsible. Is one better than the other? Better for who? No, for the searcher. Right? It's better for everybody else if it does it iteratively. Why? Because they don't have to sit there wasting time doing your search, right? It's like, but the overall resource utilization is probably better in recursive in the sense that you do distribute use of bandwidth and stuff like that throughout the system, use of computing resources. The thing is also, there's not a whole lot of difference between looking through your finger table and reporting back the next node so that the iterative person can talk to it than there is of you just sending it to the next person, right? So in other words, distributing the computation, there's actually a lot less computation that goes on in the recursive style, right? Because the iterative style, you go interrupt this person and say, "Hey, can you look up your table and tell me what the next node is?" And it says, "Oh, okay, let me look at my table. Okay, here it is." And then you come back, and then you go to the next person and interrupt them. So you're actually taking up computation time, and the only thing that you're saving that other node is, oh, well, instead of reporting that address back to you that you just asked me for, I'm just going to send the actual message to the next node because I know what the next node is. So overall, you actually use less computation in the recursive style. But the difference is that the computation that does occur is done on other machines. So hopefully in a very cooperative network, you do it recursive style, because that, again, takes advantage of all those aspects of the public computer, the peer-to-peer computing. What's this idea of virtual nodes that they talk about in here? What was that for? Right. It's to make sure that it's to even out where the keys go. So in other words, by putting a bunch of virtual nodes on a single node, what you're essentially doing is putting that node all over the ring. So there's greater likelihood that you're going to catch more of the keys. In other words, distribute the keys more. And then they kind of waffle back and forth with whether it's good and bad. And I think in most of their simulation they don't do virtual nodes and whatnot.
Is there a possibility that a virtual node could collide with a real code? Like a virtual node could collide with like an existing node, or just saw that.
Not with a high degree of probability it will not. And that's related to the 32 bits of addresses related to the 168 bits of key space. The whole good hash. Simultaneous node failures. This is all these different metrics of path length, probability distribution function of the path length in the case of a 2 to the 12th network. All these path lengths are these number of hops that you have to go through, and notice that it goes up to things like 12 and stuff like that. It goes up to 12 because it's a 2 to the 12th network, and our path length is typically log n. Right? I mean, is worst case log n, right? So that's why we go up to 12, because 12 is the log of n, right? 2 to the 12. So and that's very, very compelling. This kind of thing is very, very compelling. The PDF, probability distribution function. I don't know if any of you are familiar with these. It's basically just plotting the probability of this value of path length being any particular value. Notice that it clumps around 6, which is the center of this 0 or 1 best case to 12 worst case scenario. That this PDF is better than a PDF that centers around that peaks around 10 or 12. Why? Because if it peaks around 10 or 12, the bulk of the paths are 10 or 12, as opposed to this case where the bulk of the paths are 6. Okay, these types of things. I mean, this is what this research is all about: is creating these networks that have very, very good provable algorithms that they know terminate. They know that you can prove correctness and all this stuff. That stuff's real good. But then even more than that, in their experimental results, they show that things like path lengths are centering around 6, which is half of log n, all these types of things. That's good stuff as far as saying how chord would perform in the real world. And yeah, so that's the bulk of it. And a lot of it is talking about those different failure scenarios. But I hope this not only lets you really understand what chord does, but more than that, just how all this peer-to-peer stuff and how these peer-to-peer networks are developed. Okay, they go through, they come up with these distributed algorithms for creating the network and creating these consistent kind of primitives to do operations like find things, create keyword searches, or whatever it is your application is. All these different things. They create those. They prove that they do things like terminate and that they're correct, or scenarios where it will break and things like that. And then they run simulation. They simulate these networks and run through a bunch of random joining and failure and all that stuff, so that they can plot these things like path length, how long it takes to stabilize, all these different things. And they run experimentation so that they get the data and say, okay, look at path length. It is log n. In fact, it's better than worst case log n. This is actually half log n most of the time. The kind of unmentioned constants are 1/2 log n, which is the same as log n, but 1/2 is big when you're talking about hop 12 as opposed to hop 6. We show probability density function that says, oh, you center around 6, not around 12. Okay, this is the mechanism for computer science research. Really is. You go through, you come up with you look at these problems. How do I create a network with random peers that just by talking to one of them you can join into the network, and then I have a consistent way of talking to everyone in the network that's scalable, that's all these different things. So okay, how can I solve that? Well, here's an idea. Let's make a ring. Let's put in some pointers so that we can split the ring every time we search for something. Let's use cryptographic hashing to distribute keys around the ring. Let's use cryptographic hash to place nodes on the ring. I have a system there. Now I have chord. Let me write some stuff in like a Java simulator of running through this, all the messages that happen when things join or fail or whatever. Let me plot all the results. There. IEEE paper done. Okay? So, that's what we're going to do. Do something like that. It's maybe not creating chord, right? But creating like an application, for example. Saying, include all these clusters or whatever. How am I going to do that? Well, I'm going to break them up, right? Even building a clustering solution on top of chord is a powerful application, right? We know chord is good, right? Chord can search and log in, provably correct. There's particular scenarios where it fails, and even those can recover pretty well. Nice underpinning. Let's run it. Now let's start putting in all these different clustering modules and stuff like that. So how would we do something like that? Clustering module would be named something, hash that name, make that the key, make the map a key, right? If somebody gets the map, they'll look through the map, and the map is made up of keys, right? And it says, you need this, which is this key. You need this data, which is this key. You need this data, which is this key. Can you search for that? Yes, I have chord. I'll search for that. It'll go to a list of all the nodes that are holding that file. I'll go get it, pull it down, pull this data down, pull this Java module down that I run to do the computation. I'm going to produce something else. I'll generate the key for it, plop that on the chord network. That'll go out here. I'll go ahead and make replicas of it. See, now we have a working distributed system running an application. And we didn't even have to design the network underpinnings of it because chord did it. On the shoulders of giants. All right. So, questions, comments. Chord, good, bad? Seems pretty good. What are its weaknesses? What? Yeah. It is. It does have kryptonite. What's this kryptonite? They point out one of their comparisons with some of the other systems. One of the big things is locality. What's locality? No, not latency. Latency becomes involved eventually, but what's locality? Just the concept of it as far as data and searching for keys and all that stuff. The problem with chord is that because it's so cryptographically perfect, it always distributes everything around the ring. That's not necessarily good. Where do you want data to be? If you want that data, that's where you want it to be, right? You want it to be closest to the people that are going to use it, or get it, or replicate it, or whatever. Does chord have that property? No. Right? Yeah, it's almost the opposite. Yeah, it's like I completely ignore everything about where I'm going to place this data. Does chord put data where there's a lot of storage space? Does chord put things where there's a lot of computation? Does chord put data on the most consistently reliable systems? Can you get it to put this data on a particular system? Not necessarily, right? Who knows? Depending on how you design the higher level stuff, you may or may not be able to gain locality. Okay? If you want locality, you'll have to create an indirection layer where you go and find something and then it points to where the data is stored or whatever. Okay? But there might be nothing you can do about that key actually being on a reliable node or something like that, so somewhere along the way. Or you can arbitrarily use keys and place them where you want, but it's kind of weird, right? It's kind of against the way chord works. Okay? So, that's another key thing when looking at these papers, is one of your first things that you do should be what's wrong with this system on this paper, okay? Because see that you need to be able to read, these are to start you off, to look at the systems, understand kind of where they're coming from, the style of presenting information like they do in these papers. That's to start you off. But as we go on reading more of these papers, you need to start looking at them very, very critically and saying, what are the drawbacks? Why is this not the de facto for everything that we do in peer-to-peer networking? Okay? Because you know what? If there are no drawbacks, you're not reading a paper on it. You actually have it. You're using it somewhere, and it's always the way you do things. Okay? You hardly ever have to write papers for things that have no drawbacks, because you never have to. If something is completely perfect, you don't have to really prove it all the time, right? It'll become apparent that something's perfect. But what you need to do is be able to have these things and say, there's very, very compelling reasons to use this in particular scenarios, and here's what they are. So we need to look at them and say, where are they not compelling, so that we can decide, does this fit our application? Okay? Alrighty, so next up, for next time, actually, I noticed like you've gotten started with the Jex stuff. You sent out that stuff. I've been kind of computationally crippled this past weekend because my laptop was in the shop. They replaced the whole motherboard. So, but I got your email. I'm going to send that out. I'm actually going to. I'm thinking of what we're going to do as far as ease of collaboration, because I want somewhere that we can easily trade files and stuff like that too. So I'll probably just put up an area on my site for sending files back and forth and things like that, and then also for emailing the group. Okay, so that's good. We need to, playing with Juxta and playing around with that stuff. I'm going to try and get us by next week ramped up enough that we can start running stuff on these machines. So the idea, and you don't have to be in lab to do it. You can come in through the front end gateway and then get to these different nodes, start programs on them so that they can communicate with each other. So like I ran on all these machines for my thesis, and I ran it all from home. I just came in and then wrote batch files to start stuff up on all these different boxes. Okay, so I'm going to try and get us ramped up as far as that goes, and get the mainly the JRE updated on all these. Because I want us to be able to start getting to the point where we can write some straightforward Juxta type applications and see how they run in parallel. Okay, because I think it's very, very compelling. I don't know how many of you, if any of you have done any parallel programming or distributed programming. It's very, very compelling once you run this stuff and it runs on a bunch of machines, and it takes a fraction of the time that it took on a linear machine, on a sequential machine. I mean, you just see that and you just go, I can write anything. It's like I could solve any problem in the world. You're looking at that stuff, but that'll kind of get our so we can cut our teeth on doing these distributed applications, so that we can finally start running into the fact that no, we cannot solve any problem in the world, because there are really big problems when doing distributed computation. Okay, so for next time, I'd like you to concentrate on playing with Juxta, writing sample apps. If you have multiple machines, you can start playing around with multiple machines, but main thing is just running sequential pieces using that library for finding things or talking to things. Because you'll see that a lot of parallel programming is writing sequential pieces and then tying them together, like what I showed with that tree. It's the k-means or whatever, it's like k-means on a regular sequential machine. The only difference is that your data set's really small compared to these huge ones. It's just you're just working on a little tiny piece of a larger set. Okay, so look at that stuff, and then also continue reading this stuff in section that are tagged 1. Some of these other ones, like some of these other systems, and then also this multi-ring overlay starts getting into the idea of overlay networks, which is putting networks on top of your more fundamental network. So chord is arranged in a certain way. You could actually overlay a network onto it to get different structures like hypercubes and stuff like that, so that you can change how they talk to each other, whether they can broadcast, stuff like that. Okay? Because what you're doing is once you build on this foundation of having very basic primitives, and then you can do more complex services on top of it. Okay? That's it. Okay? But start playing with Juxta, compile some programs and things like that. So that's what I'm interested in next time, is we're going to talk more about Juxta and actually using it and writing some programs. Huh? Okay, so I mean, have you guys run into anything in particular with it, or? So some of the tutorials in that, yeah, it's a huge manual that they have on there. I wanted to print it out, but then I looked at it, I was like, where am I going to cut it? Because it's like 150 pages or something like that. And I didn't want to, even if I print out 150 pages, that'd be wasted. I'd never carry around 150 pages of text.
It's the same.
Yeah, just different examples and different ways of talking and like
Well, they
different.
build up on it, but once you make it like the fourth one,
Yeah.
it's all the same after that.
Okay. So just look at it and kind of see what its features are as far as it's just a way of talking, of finding and talking to nodes. And you'll see that all of peer-to-peer is that is, how can I talk to a lot of nodes without keeping track of a lot of information? So that's what it does. Alrighty. But I'll put together a mailing list so that we can correspond easier as far as sharing notes on this stuff. But start looking at Juxta and start thinking about what you think you can write in a semester as far as creating some applications with this. Okay. Oh, and also there's an ACM meeting today. It's on neuron databases that it's somebody postdoc at in the Department of Biology. Some of the I don't know if this is the same project, but a lot of the computer science faculty is some of the computer science faculty under Sundaraman is doing a lot of stuff with this type of thing. These neuron databases. Like he's doing all kinds of crazy stuff with I think Dr. Zhu about they have like this interface where they touch points on like a crawfish's brain or something. They touch points on it, and that will query the database for neuronal information of research that's been done on that particular set of neurons. I don't know. Like you hit points on the brain, and that's your query. Your query is these points, and it'll say, "Here's all the neuronal information I have related to that area of the brain that you just touched on." So it's kind of crazy stuff, and it involves like a lot of like, not only like really hardcore theoretical database stuff, which is obviously why Dr. Sunram is involved, but also like the actual interface and image recognition and all that stuff is involved as well, the 3D modeling. So it's pretty crazy stuff. It's over at it's over in the Student Center, Capitol Suite 220. Yeah. Yeah, and there is free pizza.
Went to the last ACM meeting, but it's really weak. There's some guy talking about security, but it was just like the most general, obvious ideas about security ever. It was like nothing technical whatsoever.
Oh, okay. Yeah, they're kind of they kind of bounce as far as like what the topics are. Sometimes it's like really hardcore technical. Sometimes it's more business oriented because
That's what it does.
CIS is associated with ACM as well. They don't really do a lot, but they're technically part of the I guess the sponsors of ACM. But they they obviously have a lot more business. And plus, a lot of people who go to ACM. ACM is a great place to look for jobs because they'll even have speakers come in who are recruiting who have positions open. So it's kind of back and forth. And then there's days like today where it's like a postdoc who's going to sit there and talk about stuff that's like
I want to go.
really hard.